Okie dokie, artichoke. We had a couple due for review on Wednesday. Well, here we are on Wednesday. This is section 8.2 continued. We introduced all these topics, but we'll use them for review. We talked about the union of two events, for example. And so if two dice are rolled and the events F and T are as follows, if F is the sum of the dice is 4, and T is at least one die shows a 3, we want to find the probability of F or T, right? This is or. Now it might be helpful to remember from last day. I'll make this bigger here slightly. And on your formula sheet, the addition rule that says this. Generically, the probability of E or F is the probability of E plus the probability of F minus, so we have to subtract the overlap, which is the probability of E and F. And so I'll clarify here that this is our and notation. And I remember it because it turns into kind of an A if you draw a line, and then the other one is or. I'll remove that because that might get confusing. This is in terms of general E and F, and we want to map it to, confusingly, F and T. So wherever you see an E in the original equation, you're going to replace it with an F, and wherever you see an F in the original, you'll replace it with a T. So just be really careful when you map these. So we want to find the probability of F or T. And how we're going to do that is we want the probability of F plus the probability of T. Notice that it's just the first one and then the second one minus the overlap, right? And so probability of F and T. This looks too pointy there. So if we want to find the probability of F or T, we need all of these three probabilities, and we can find them. And I've pasted the results of two dice being thrown, right? So two dice are rolled, and we're talking about the sum of the dice and what the die, at least one die shows a 3. So for F, I'll use orange for events in F. And I'll use, what color? Maybe green to circle events in T. And my go-to pink for events in F and T. We need to know how many events are in each, or how many outcomes rather are in each event. And out of 36, because we have 36 different options. All right. F. The sum of the dice is 4. Okay. That happens here, 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 and I don't see any more. T, at least one die shows a 3. Okay. Now, at least one die means 1 or 2. right? And so as long as it shows a 3, I'm going to circle it. Now I'm talking about the die, right? Not the sum for this one. And so for the events in T, I want the events that are in that have a 3, which is going to be all of these guys. That's 2 3s and at least 1 3. Now there are 2 that we've circled twice, which means that they're going to be in F and T. Right? And so here, there, and here. 3 1 and 1 3. All right. Let me just. So from this, the probability of F is how many orange circles I have divided by 36. So I have 3 over 36. The probability of T is how many green circles I have divided by 36, which is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Making sure you don't count the 3, 3 twice, right? Because it's overlapping. So 11, right? I think I said, yeah, 12 minus 1. And then finally, oops, the probability of F and T, I have 2 that are overlapping 2 out of the 36 outcomes. Now we can put these together and we can find the probability of F or T. Oops. It deleted stuff. There. Probability of F is 3 over 36. Probability of T is 11 over 36. And probability of F and T is 2 over 36. Now, because I have a common denominator, it'll be cleaner to just keep it as a fraction. If you're not comfortable working with the fractions, you can absolutely turn them into decimals. As long as you keep a good chunk of decimal places, like 4 or 5, I would say, just in case, right? But I'm going to keep it as a fraction just because we can. How do you add a fraction? Or how do you add fractions? You have to make sure you have a common denominator, which we do, and then you're allowed to just add across the top or subtract if you need to. 3 plus 11, 14 minus 2. I'm going to go for 12 over 36. Which should also match let's see here. What was I going to say? It's okay. I lost it. I just stare at it long enough. Ah, that's okay. We're good. Nice. The probability that the sum has a dice of, I'm trying to get there. I'll just give up. Any questions about that one? a nicer way of asking the same-ish question is like this instead, right? I'm not going to ask you the sum of two dice questions because then I'd have to give you the table and it's a lot of extra printing that we don't need to do. So this is kind of more reasonable, in my opinion. Mr. Washington is seeking a mathematics instructor's position at his favorite community college in Cupertino. His employment depends on two conditions, whether the board approves the position and whether the hiring committee selects him. So, of course, both of those have to happen before he can get a job. There is an 80% chance that the board will approve the position, and there's a 70% chance that the hiring committee will select him. If there's a 90% chance that at least one of the two conditions, the board approval or his selection, I'm going to highlight or underline this or, will be met, what's the probability that Mr. Washington will be hired? So, what we want to do is first define some shorthand, right? We've got two events that we're talking about, and so the board has to approve the position, and then the hiring committee has to select him. And so I'm going to let capital B be that the board approves the position. And what should we use? Let's use H for the hiring committee. Double M, double T, double E. Wow. Selects him. If you define your shorthand, you can always use shorthand like that. So now we want to figure out, okay, well, what we've been given some information. We'll start with the first number. There's an 80% chance that the board will approve the position, which tells me that the probability of B must be 0.8. Remember, probabilities have to be between 0 and 1, so you don't want to use 80, even though in our writing we usually use percentages, but for our math we want to use decimals. Next piece, there's a 70% chance that the hiring committee will select him. And so that's going to be the probability of H, which is 0.70. If there's a 90% chance that at least one of the two conditions, so the board approval or his selection, that means that we're given the probability of B or H is 0.90. What's the probability that Mr. Washington will be hired? Well, hiring means B and H, right? The board has to approve the position and the hiring committee has to select him, of course. So we want to find the probability of B and H. Now we've seen all these components before, right? As soon as you have the probability of B or H, usually you're going to be using this formula that we saw. All right, this one here, which I'll bring in again. Copy. Whenever you see an E in the general formula, you'll replace it with a B, and an F in the general formula, you'll replace it with an H. Right? Now, we have the probability of B or H is the probability of B plus the probability of H minus the probability of B and H. Buh. If I give you any three of those four components, you can solve for the fourth one, right? And so in this case, we have 0.9 is probability of B or H. Probability of B was 0.8, and the probability of H was 0.7, and I want to solve for the probability of B and H. I'm going to rearrange. Now, I don't like dealing with negatives, and so I'm going to add the probability of B and H to the left-hand side, and in the same maneuver, I'm going to subtract 0.9 from the right-hand side. And so I get the probability of B and H is 0.80 plus 0.70 minus 0.90. All right, this guy went over here and this guy went over here. All right. 0.6, I'll confirm, but the probability of B and H, the probability of him being hired effectively, let me check. 0.8 plus 0.7 minus 0.9. Phew. 0.60. So that's the probability that Mr. Washington will be hired. There's that blabbing. Why does it keep glitching? It's not a good sign. I know the e-building had a crazy power outage.
Yep.
Did you guys have classes then?
Yeah, I had it in the C building, and then ours glitched. We were doing a lab test, and the light went off for like 30 seconds, and our prop was like off. And then it came back on. I was like, darn it!
The e-building was out for like all day, I think.
Yeah.
It's crazy. Crazy.
When you know, like they happened, all this happened on thing. So guys, please just open on the little thing. I'm like, okay. But if it's a power outage, then don't you know how internet? So did they just expect? Okay.
Yeah, I don't.
And they just expect everyone to have a hotspot.
I don't know. Or maybe they have a wide enough range or something. Who knows? I'm glad it wasn't during our class. The probability that this weekend will be cold is 0.6, although it hasn't been very cold, has it? And the probability that it will be rainy is 0.7, and the probability that it will be both cold and rainy. And I want you to kind of pay attention to those ands and ors, right? What's the probability that it will be neither cold nor rainy? That's a tricky one. Let's start by defining some shorthand. Let C be that it's cold and R be that it's rainy. Just because I don't want to write those out. That's it. And we're given the probability that it's cold is 0.6, and the probability that it's rainy is 0.7, and the probability of cold and rainy is 0.5. We want to find the probability that it's neither cold nor rainy. Now, it does require a little trick, which would be on your formula sheet if you had to do it on the final exam, which means you don't have to do it. So I'm just going to give it to you. We have seen De Morgan's laws before, but what we want to find, neither cold nor rainy, is the complement of cold and the complement of rainy. So it has to be both cold and, I did that weird, or I did it wrong actually. Rainy, the complement of rainy. I was trying to read it. Now, as a fact, the complement of cold and the complement of rainy is, I did it again. It's because I'm, yeah, I don't know. Reading them and writing them. Can't do both, I guess. The complement, or C or R, there. Ready. That's a fact. It's called De Morgan's laws. We saw it in logic, right? Where if, let's start in here, if we're distributing the complement inside the brackets, then it basically just flips the sign and vice versa. This is not something that you need to know. We need it for this question, but for the final exam, I'm not expecting you to know it. It would be on your formula sheet if I did. But it's not. So what that means is we can find the probability of C or R and then take the complement of it. So we can we first find the probability of C or R, which is the probability of C plus the probability of R minus the probability of C and R, which is 0.6 plus 0.7 minus 0.5, 0.8. I'll confirm. Therefore, the probability of the C or R complement is 1 minus 0.8, which is 0.2, which is the probability that it's not cold and not rainy. Kind of sneaky.
Why does it say minus the probability of CC and R?
Oh,
Wait, never mind.
one's a bracket, but it's looking a lot like a, there. Do it a little bit more upright. It was looking a lot like a C. Nice. So that one's a little sneaky, but that's okay. Any questions about that one? Besides my brackets. No, don't want to stress you out. tree diagrams.
They're so fun, but they take up so much space.
They do. They do. Well, lucky for you, there will be a tree diagram on the final exam. There will.
That means I'll get at least one favorite.
So tree diagrams, we've used tree diagrams to map out the sample space, right? To map out all the possible combinations of outcomes, right? For each event. And so now we're just going to change it slightly and use the tree diagram to map out probabilities instead. And so we'll still have each outcome, but each outcome happens with some probability, right? And so what we're going to do is we're going to put probabilities to, or attach probabilities to each event on the branches of the tree. Okay. And then we're going to multiply probabilities along a path through the tree, which means that we can find the probabilities for AND events, because AND is multiplication. And add branches to find OR probabilities. I'll add that here, so it's all there. Let's have a look at an example. You have a jar, you have 3 red marbles and 4 white marbles, and if 2 marbles are drawn with replacement, what's the probability that both marbles are red? So let's start with just the outcomes, right? We can make a tree diagram here. So I draw my first marble, marble number 1, and it can be red or it can be white. And with replacement, oops, marble number 2 can be red or it can be white. It can be red or it can be white. This is red. So down here, right, we can still write out our sample space. And in fact, I encourage you to do that, right? Just so we can look at what all the different combinations are, WR and WW. Now we're going to also write probabilities at each branch, right? Drawing a red happens with some probability, and that probability is not necessarily the same as drawing a white marble. In fact, here we have a total of 7 marbles total. So the probability of drawing a red marble is going to be 3 out of 7 for my first marble. And the probability of drawing a white marble is 4 out of 7. Now, technically, so this is how I show my work. It's very sloppy because technically we should write the probability of R is 3 over 7. No thanks. I don't expect you to do that. Technically, we should. So I say what the outcome is, and then I write down what the probability is. Now we're sampling with replacement. So if I drew a red one, then the red one goes back in and it stays the same, right? 3 over 7, and I still have 4 over 7 white ones. And same thing on the other branch. Hmm. When we write RR, right, really what we mean is R and R, right? Marble 1, marble 2, a red and a red, right? A red and a white and a red, a white and a white. And so really what this means is R and an R. And for probabilities, what that means is we can multiply down the branches, right? And we can find a total probability at the end of this branch. And so we can write the probability of RR, and I usually drop the and, is going to be 3/7 times 3/7, which 3/7 times 3/7 is roughly, now I'm going to round here. Let's keep 4 decimal places, 0.1837 to 4 decimal places. Yeah.
Why do you have 3/7 times 3/7? Because there's 3/7, but there's only one RR.
It's because I'm working only on this branch right now.
Okay.
And so to get to the bottom of this branch, I had to go through 3/7 and 3/7. And so this is your and here. So at the end of each branch, you'll have, if you multiply down each of the branches, then you'll have the and probabilities, right? The total probability of ending up at that branch. And for the next one, right, I'll show you how sloppy I am when I write out my work. I do write out what the combination is, right? RW versus WR versus WW. Okay, but at the end, all I do is I just write down what the probability is. So I don't use proper notation, I guess. But proper notation at this point is kind of overkill. So I write 0.2449, keeping just 4 decimal places. So for each of these, I'm going to do 4 decimal places. Yeah.
And then I see 4 R's and 4 W's. So why is the R's only 3/7, whereas the W's is 4? I know it makes up to 7, and that makes sense logically, but if you were to have doubles.
It's because you have 3 red marbles and 4 white marbles that you're drawing from. And so it's from here. How many did you have? How many do you have in your, I don't know, jar? Usually it's an urn for some reason. A jar. So now if you draw a white one first and then a red one, right, with replacement, then that should be the same as drawing a red one and then a white one, but let's confirm, right? So 4/7 times 3/7 is 4/7 times 3/7. It is the same, 0.2449. And then 2 white ones, 4/7 times 4/7. We get 0.3265 to 4 decimal places. Now here, bless you. So usually I would just write 0.1837, but I wanted to show you where it came from here, right? And so, bless you.
I swear to this group. Literally, this is the only group.
I think it probably has like pretty powerful vents and stuff.
Yeah.
It's like, yes, yeah. And also, 'tis the season. What was I gonna say? Oh yeah, so here, this is our sample space, right? And so these are all the possible outcomes if I draw two marbles with replacement. And what do I know? We also recall on your formula sheet, the probability of the sample space has to be 1. And so a nice way of checking your work with your tree diagram is to make sure that the sum of these probabilities has to be 1. And now if you've rounded values, there's a tiny bit of wiggle room, right? If you get to 1.0001 or something like that, then that's okay, right? Or 0.9999, right? And so to check our work, we add the probabilities in the sample space to make sure they add to 1. So what I mean by that is 0.1837 plus 0.2449, 0.1837 plus 0.2449 plus 0.2449 plus 0.3265. This over is 0.1837 plus 0.2449 plus 0.2449 plus 0.3265 is 1. Yay. Why are we adding? Because the sample space could be R and R, or R and W, or W and R, or W and W. And so whenever you're saying or, right, or in between here, that means addition. That's for the sample space, but that'll apply to any probabilities that you want to combine. Now, I think for here, we wanted to know what's the probability that both marbles are red. Well, that's the answer here. The probability that they're both red is 0.1837. And then I took it further to introduce the sample space as well. So I'll say here, this is the answer. And then talk some more about some stuff. A lot of stuff. Nice. Any questions about that one? Oh, maybe I'll need more space than that anyways. If we have the same example and the two marbles are drawn without replacement, so that changes some things, right? Without replacement, then what's the probability that both marbles are red? So it's the same question, it's just without replacement instead of with replacement. Now, it's going to be, I'm going to cheat here and copy this. Clean it up. And this will be changed anyways. So now we're sampling without replacement, which means that I need to change my second marble probabilities, because then it'll be conditional on what happened with the first marble, right? And so let's tackle the denominator first, because if you have 7 marbles to start and then you've drawn one without replacement, then of course you only have 6 left, right? And so for your second marble, the probability is going to be just out of 6 for each of these. Well, since you've removed one and you didn't put it back. Well, now the numerator, right, depends on what, and later we'll start calling that is conditional on what the first marble was. Okay? And so if you draw a red marble first, then there are only 2 marbles for the second one, or sorry, 2 reds for the second marble. And there are still 4 white ones. If you draw a white marble first, then there are only 3 white marbles left, and there are 3 red marbles left. So now you can do 3/7 times 2/6. I'll do 4 decimal places again, 0.1429. 3/7 times 4/6. 0.2857. And 4/7 times 3/6 is 0.2857 again. And 4/7 times 3/6. I get 0.2857. Make sure that I'm happy with my probabilities here, which I'm going to use to answer a lot of other questions. Let's make sure that they all add to 1, or at least roughly 0.1429, since we did some rounding here. 0.2857 times 3 equals 1. So that's good. Just as a little check-in point. We wanted to know the probability that both marbles are red. So the probability of red and red is 0.1429. On the final exam, how the question will be set up is just like the Venn diagram. It'll get you to make the tree diagram first, and then ask you a couple of different questions using the tree diagram. And so we have Let me move these down. Some more parts using this same tree. We have the same jar with the same marbles, 3 red and 4 white marbles. If 2 marbles are drawn without replacement, find the probabilities using a tree diagram. Now this is the same tree, so that's what I mean by once you've made the tree, you can use it to answer lots of different questions. And so here I'll say same tree as 8.3.2 above. Maybe. Also. We already confirmed and found all the probabilities, and so now we can go ahead and use them. They love this question. The probability that both marbles are red. We've answered that like 3 times already. The probability of red and red, 0.1429. What if we want to find the probability that the first marble is red and the second marble is white? That's going to be the probability of red and W. Which if you use your tree, the first one has to be red and the second one has to be white, which is 0.2857. Whoop. The probability that one marble is red and the other marble is white. Now, there are 2 ways that I could have that happen, a red one and then a white one, or a white one and then a red one. Right? And so what that's going to look like is the probability of a white one, or sorry, I'll do the same order. RW or WR. If you replace the or with the union, that's the same as the probability of RW plus the probability of WR, right? And so that's where we get this idea that, okay, if you are saying or in between, then you add the branches that apply. So I have the probability of RW and I have the probability of WR. Now, there's no overlap here, right? The probability of both of those happening at the same time, if you're only drawing one marble and then a second marble, the probability of the overlap is going to be 0. And so you can still write it, probability of R, W, and WR is going to be 0.2857 plus 0.2857 minus 0. And I'll sneak the answer on the same page here. Point 2857 plus 0.2857. 0.5714. Nice. Now we saw combinations, which is the choose function, right? NCR. We can use the choose function to find probabilities. It's going to be especially useful if you're looking at a tree diagram and you're thinking, man, I don't want to build this because you might have, 4 or 5 different layers to it, right? And it's just too big. Then you can use the choose function instead. And so tree diagrams do help us map out a problem. And so, but tree diagrams are not practical for problems where more than 2 or 3 things are chosen. So more than 2 or 3 marbles, for example, right? And so more than 2 or 3 things are chosen. So layers of the tree diagram. So if you find yourself, oh, okay, drawing 4 marbles, for example, then that's crazy, right? Even if you only start with 2 colors, but what if you start with 4 colors? Oy, yikes. That's terrible. So what I want to do is move this down, but also I want to solve this problem first with a tree diagram, and then I'll show you with the choose function, and so that you can see the connection between the two. If we have a jar with 3 red, 2 white, and 3 blue marbles, and if 3 marbles, it's kind of borderline, are drawn without replacement, find the following probabilities. So what I'm going to do first, right, is I'm going to draw the tree diagram. Now, I have 3 colors to start, and then I'm drawing 3 marbles. So what I need to make sure is that I give myself lots and lots of room at the start. So here, this is marble number 1. I'll make a note here. We will solve with a tree diagram. Oops. Then with combinations. So we start with a red and a white and some blue marbles. I'm going to map out the different scenarios first, and then I'll attach the probabilities. And so marble number 2, 1, 2, 3, 1, 2, 3, 1, 2, 3. Red, white, blue. red, white, blue, red, white, blue. Now marble number 3, I think I said 3. And I'm tired. I need a little bit more room here because I need room for 3 branches off of each of these 3 branches. So this is where you start to think, I don't really want to build this tree diagram. Maybe there's a better solution, and there is. So don't worry, but we'll do it just for practice. Well, maybe I can copy paste. Copy. Not really. I made it too tight. I overcommitted. Luckily, I have copy and paste. You can imagine. I will write in red. Don't do this. We will, but don't do this. Or maybe we won't. It's looking really tedious. You can attach the probabilities though. Let's do it for the first 2 marbles, and then I think you get the idea for, this is marble number 3. If you have 3 red, 2 white, and 3 blue, then you have 8 marbles total to start, which means that you have a probability of 3 in 8 to draw a red, 2 in 8 to draw a white, and 3 in 8 to draw a blue on the first marble. Now, without replacement, and for this section, I made a note on the exercises that you're submitting. So sometimes it's unclear, but if it is with replacement, it has to say with replacement. And so otherwise you can assume it's without replacement. Without replacement, if you've drawn a red and you've drawn a marble and you're not replacing it, then you have 2/7 remaining. And 2 white ones still, 2/7, and 3/7 for the blues. And I'm going to cheat and say etc. for the rest of them because yikes. I won't ask you something. Yeah, etc. No. The biggest I would do is 2 marbles. So we could do 3 and then 3, right? 3 colors, but only 2 marbles. It's the third marble that really kind of pushes us over the edge. If we had only 2 colors to start, it'd be a little bit more reasonable to do 3, but and so that's why for problems with where there are more than 2 or 3 things being chosen, in this case 3 is way too many, right? Then we're going to use combinations instead. And so let's map out a 2 red and 1 white. That could happen here, here, here. Oh, sorry. And 1 white. Or a red, white, and a red. Or a white, a red, and a red. Or or not a blue. So you could only map out those probabilities, and let's maybe do that because I'm feeling okay. Skimped out here. This is only for A. If I've drawn a white marble and I have 7 marbles total now, there are 3 red ones, 3 out of 7, 1 out of 7, and 3 out of 7. I'm only going to do the probabilities for the 3rd marble that I need. And so now I've drawn a 2nd marble, which means I only have 6 marbles to draw from left. And if I've drawn 2 red ones already, then I still have 2 white ones. For the next set of branches, the red, white, and red. If I have drawn a red already, then I only have 2 red ones left. 2 out of 6. And for the last one that I need, a white one, a red one, and a red one, which means I only have 2 out of 6 red ones left. I stand by that don't do this, but I'll move it down just a smidge. Because at the end of each of these, right, I can write my combinations, RRW, RWR, and WRR. Hey. Below each, I can find the probabilities. 3/8 by multiplying down each branch and all the way to the very end. And so 3/8 times 2/7 times 2/6, rounding to 4 decimal places, 0.0357. Next branch, 3/8 times 2/7 times 2/6, 0.0357. Should have known. Let me guess, 0.0357. We'll do it. 2/8 times 3/7. Why are they all going to be the same? Because it doesn't matter what order you multiply things in, right? They'll always be the same. 0.0357. So for A, the probability of 2 red and 1 white is the probability of RRW, oops, or the probability, or RWR, or WRR. Now, because there's no overlap, they're mutually exclusive, right? And so then you are allowed to just add the probabilities. So it's going to be 0.0357 plus 0.0357 plus 0.0357. Did I miss any combinations? No, no. All right. 0.0357 times 3. I get a probability of 0.1071.
Why is the second one not 0.0357?
It is. Because I just stopped. So this, I feel like, is way too long. And so what's our alternative then? Here it is. Do this instead. For probabilities, right, the probability of 2 red and 1 white is going to be, just in general, what we know about probabilities is the number of outcomes that satisfy the 2 red and 1 white. Right, and so the probability of oh no, not the probability. The number of outcomes with 2 red and 1 white divided by the number of ways that I could draw 3 marbles total. Right? The number of ways we could draw 3 marbles. And maybe I'll say from 8. Now, sorry, I just want to confirm something. Please stay on the line. Let's start with the number of ways that we could draw 3 marbles from 8. And so that's any 3 marbles out of those first initial 8 marbles, right? Because we had 3 plus 2 plus 3 marbles, which makes 8 total. So that's where that 8 comes from. Same as in the denominator in the tree. This, you might remember, you can find by doing 8 choose 3. Right? The order doesn't matter. How many ways can I choose? Just 3 marbles out of 8. 8 choose 3 on your calculator is 56. Now, the trick is the number of outcomes with 2 red and 1 white is going to look like this. This is where we need to get specific. From the red ones, so from the 3 total red ones, I want to choose 2. 3 choose 2. And 1 white one, so from the 2 white ones, I want to choose 1. 2 choose 1. Now, and, of course, means multiplication. And so 3 choose 2 is 3. And 2 choose 1 is 2, which then puts me at 6. So then the probability of 2 red ones and one white one is going to be 6 over 56. Let's try it. I get 0.10714285571, which is great because that feels a lot quicker than building the tree and then using the tree and mapping out all your outcomes. But we do get the same answer. Right here, we used rounded values, right? And so we only get a rounded value for our answer, but it's the same. Same answer. So the trick is to find the total number of ways that you could just choose 3 marbles from the 8 and use that as your denominator, and then do the different combinations that you want, right? So let's try another one. You want one of each color. You can do that with the tree, but that sounds terrible. Right. That's going to be one red one, one white one, one blue one over the total 56, which is the same 56 for all of these. So this is going to be the probability of one red and one white and one blue. I keep doing the probability, sorry. Over 3 from 8. Or 8 choose 3. Maybe I'll just write it properly. So to choose one red one, that's going to be 3 choose 1 times one white one. There were 2 white ones initially, 2 choose 1, and 1 blue one. There were 3 blue ones initially, 3 choose 1, divided by 8 choose 3. 3 choose 1, we said was, oops, P1 was 3. 3 times 2 times 3 divided by 56. 18 out of 56. That's technically your answer, but sometimes it's nice to show the decimal. 0.32142857. Nice. How am I doing for? Whoop. Okay. The probability that none are blue. Okay. You want the probability that none are blue. If you go back to your tree and just kind of vision quest it, right, then there are lots of different options where there is none blue ones, and I'm seeing too many, and I'm trying to think of the best way to solve it. None of them can be blue. none of them can be blue. I knew this would happen. I brought my cheat sheet. Let me look. Because I was overthinking it. None of them can be blue. Oh man. Then I only have 5, 3 white ones and 3 red ones and 2 white ones left. Which means I have 5, choose 3 non-blue ones. Blue options to choose from. There we go. Divided by 8, choose 3. 5, choose 3 is 10. Divided by 56. 17857. Fine, 14286. This is the one that I was thinking of. If you want the probability of at least 1 blue, now the trick is when you see at least 1, it's usually easiest to use the complement instead of actually doing the at least 1. No? And so it is usually easiest to consider the complement. Complement. It's a complement. So the probability of at least 1 blue is the probability of 1 blue plus the probability of 2 blue plus the probability of 3 blue. Oops. Now, you can find the probability of 1 blue and 2 blue and 3 blue. Let's do it. I'll need a lot more room though. The probability of 1 blue is 5, choose 2, which are the non-blues, and 3, choose 1 for my blue. Non-blue, and here's my blue, forcing the blue, over 8, choose 3, plus, if 2 of them have to be blue, then 1 of them has to be non-blue. 5, choose 1, times 3, choose 2, divided by 8, choose 3. And then for 3 blues, then I have 3, choose 3 ways. 5, choose 0 is 1. So I'll write that down. Oops. 5 choose 0 times 3 choose 3. 8 choose 3. Oh. You can do that. Seems like a lot of work though. Right? But you can do it, you can brute force it. And so let's see here, 5 choose 2 is 10 times 3. Let's just go for it, 30. 3 choose 2 times 5 is 15. And 3 choose 3 is 1 all over 56. 30 plus 15 plus 1 is 46 over 56, which is roughly 0.8214285714. I'm gonna try to keep it on this one page here. So when you see at least one, this is the correct way of doing it, right? But this is a lot of work, right? And so here, or with the complement, what you get is the probability of at least one blue. What's the complement of at least one blue? That would be 0 blues. 1 minus the probability of no blue. Or how did it say? None blue. Use the same terminology. Now we found the probability that none of them are blue earlier. Right? Found in part C. And so this is going to be 1 minus this guy. One minus 0.17857142886. And can I squish anything? I'll just put it here. 0.82142.85714. Whee, which is the same. But using the complement is a lot easier. But you do have to remember that trick. Otherwise, you get the same answer. It just took you a lot longer. Right? So that's okay. It does require the probability that none of them are blue, which for some reason stumped me briefly. I'll admit. But that's a lot quicker or a lot easier math than all of these guys put together. Oh. Nice. Which way? See? There? You got it. Nice. How much time do we have? Okay. This one's a little bit tricky, but I want you to see it in action so that you can solve something similar. But I would say it's a little bit too hard for a final exam question, but just so you've seen the problem solving. 5 cards are drawn from a deck, and we have the deck of cards from last day. Find the probability of obtaining 2 pairs, which is, of course, 2 cards of one value and 2 of another value, and then 1 other card. How I would recommend solving this is, maybe it helps to bring in our deck of cards. Where is it from last day? Copy. There. So if you're drawing 5 cards, then a pair of cards would be, maybe you have a pair of aces, which means you can't draw another ace, right? As a second pair. We're assuming that the first pair is of one value and then 2 of another value. Otherwise, you'd have 4 of a kind, which is a different hand, but you could have maybe a pair of 3s, for example. And so what I want to do is consider that special case and then see what we need to do to extend it to all the other pairs. And so maybe in this scenario, we have just drawn a 5 as our single. So we've got 2 aces, 2 3s, and a 5. So consider 2 aces, 2 3s. I'll write it out. And 1 5. Now there are 4 of each of these to choose from. Just make sure I'm on the right track. Yeah. Which means that if I have the probability of 2 aces and 2 3s and 1 5, I should use words, shouldn't I? From the aces, I have 4 to choose from, right? So 4 choose 2. That's my ace, or my 2 aces. And I need to draw 2 3s, and there are 4 of those. So 4 choose 2. This is my 2 3s. And from the last card, this card is from all the remaining 52 minus, I can't draw an ace and I can't draw a 3, right? And so 44, 52 minus 4 is 44. Choose 1. One other. I guess I don't need to specify the 5. I can just say 1 other. Oops. I'll delete my highlight on the 5. And I'll clarify this 44. Since 52 minus 4 equals 44. I can't draw an ace and I can't draw a 3. And this is over the total of 52 cards. Choose 5. Hand of 5. So 4 choose 2 now is 6 times 6 times 44 choose 1 is 44. And then 52 choose 5, which I'm pretty sure you've solved before, right? How many ways can you draw a 5 card? And 2, 5, 9, 8, 9, 6, 0. 6 times 44. 1, 5, 8, 4 over 2, 5, 9, 8, 9, 6, 0. Very small. 2, 5, 9, 8, 9, 6, 0. I get 0.0060947455591. Like, same. That's for this specific hand, right? 2 aces and 2 3s. But now we need to extend it. Now we need to extend this scenario to any 2 pairs. And in terms of my pairs, right, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different suits that I can choose 2 sets of pairs from. And so I get to any 2 pairs from 13 suits. Which means I get the probability of 2 pairs and 1 other is 13 choose 2 times this. Being lazy. Mostly because it's on my screen already on my calculator. So now I'm just going to go times 13, choose 2, and I get a probability of 0.047539016. So the probability of drawing 2 pairs and 1 other card is roughly 4.75%. Pretty low. Nice. Nice. Any questions about that one? That one's sneaky. Especially this part, I think. First part, not so much, but the second part is, in my opinion. And then for some reason, we go back to what I would consider a way more reasonable problem. A cell phone store receives a shipment of 15 cell phones that contains 8 iPhones and 7 Android phones. Suppose that 6 cell phones are randomly selected from this shipment. Find the probability that a randomly selected set of 6 cell phones consists of 2 iPhones and 4 Android phones. So whenever you just want to have a grouping like this, it's going to look the same. The probability of 2 iPhones and 4 Android means that from the total iPhones, 8, I need to choose 2. And from the total Androids, 7, I need to choose 4. And from the total shipment of 15, I need to choose 6. Eight choose 2 is 28, 7 choose 4 is 35, and 15 choose 6 is 5,005. 8 times 35. 980 divided by 5. 0.195804195.8. This one feels a lot more reasonable for a final exam. Something like that. Nice. Or like this. One afternoon, a bagel store still has 53 bagels remaining, 20 plain, 15 poppy seed, and 18 sesame seed bagels. Suppose that the store owner packages up a bag of 9 bagels to bring home for tomorrow's breakfast and selects the bagels randomly. Find the probability that the bag contains 4 plain, 3 poppy seed, and 2 sesame seed bagels. So here we go again. The probability of 4 plain and 3 poppy seed, I'll just do poppy, and 2 sesame. From the 20 plain, I have to choose 4. And from the 15 poppy seed, I have to choose 3. And from the 18 sesame, I have to choose 2. And from the total 53, I need to choose 9. Notice that the 20 plus 15 plus 18 makes 53, and the 4 plus 3 plus 2 makes 9. Right? And so they'll have that relationship always. Otherwise, you're missing something. 20, choose 4 is huge. 48, 45, 15, choose, oops, 15, hey, 15. Oh, I keep hitting the wrong button, that's why. 15, choose 3. It's 455. And 18, choose 2 is 153. 53, choose 9. It's huge. 4, 4, 3, 1, 6, 1, 3, 5, 5, 0. 4, 8, 4, 5. I'm just gonna do it times 4, 55 times 153 divided by that guy. I get an answer of 0.07610877742. Nice. Questions about that? So hopefully these two feel reasonable. It's kind of the extent that I'm looking for on the final exam. We'll do the birthday problem real quick because it's the last one. And it's a really fun one. But it's also too hard to do on the final exam. Oops. Moved it. Can't move it. So the birthday problem is finding the probability that two people in a room have the same birthday. And it turns out that you don't need a ton of people in a room, even though there's 365 days in a year, you don't need very many people in a room in order to get a high probability of having the same birthday. And so that's what's commonly called the birthday problem. I just want to show you how to solve the birthday problem because it's kind of fun. So if there are 25 people in a room, which again is not a lot of people, what's the probability that at least two people have the same birthday? And so again, we have the at least two. And whenever you see at least, I want you to think complement. What's the complement of at least two having the same birthday? Probability of at least two is 1 minus the probability that none have the same birthday. So if we focus on the probability that none have the same birthday, how would you solve that? If there's 25 people, right, then for your first person, you have 365 choices. Second person, you have 364 if they can't have the same birthday, right? 363, for 25 people. Right? That's a lot. But we know how to solve that. What's that? That's 365 P25, right? Permuted in 25 different ways. And so that's going to be 365, oops, can't write anymore, P25. All right. Stop once you've filled 25 slots. Divided by the number of potential birthdays that you have, which is 365 times 365 times 365, 25 times. And so you get 365 to the power of 25. That's kind of the leap, but I'm just giving it to you. So then the probability of none, let's see if my calculator will even do 365 to the power of 25. Okay, it does, but it's huge. How about 365 permuted 25 ways? Quite large as well. It's going to be in scientific notation. Oh. 4.921543,949 times 10 to the power of 63, which is huge. And 365 to the power of 25. 1.141094498 times 10 to the 64. And I want to do 365 P25 divided by that. I get a very reasonable 0.431300296. That's the probability that none have the same birthday. It's high, but it's not that high. And so what that means is that the probability of at least 2 people having the same birthday is 1 minus 0.431300296. So 1 minus that, which means it's roughly 0.5686997. From here, you could adjust the number of people that you have, right, and find the different probabilities. But what you'll find is that pretty quickly you reach a probability over 80%, which is kind of cool. Anyways, I see he's at the door already. So if you have any questions, let me know. Otherwise, enjoy your weekend. Last week of classes, oh my gosh, it's crazy. Next week, I should say.